two indexes, totally different failure modes. Pick wrong, and you'll burn latency or RAM. This is the final pipeline that tunes index choice on your texts, then searches a query so you get faster answers. You will learn to balance speed, memory, and accuracy. I'm Professor Pi, teaching search and IR with simple Python. Searching with embeddings is great, until it is slow or expensive. You store vectors, and then ask which items are nearest. Success means queries return fast, results are relevant, and cost stays sensible. pgvector in PostgreSQL is a convenient place to do this because it keeps vectors close to your data, and SQL gives you control over indexes and settings. At a high level, the playbook is about picking the right index for the right workload. Exact search returns the perfect nearest neighbor, but scans cost CPU as your table grows. Approximate indexes cut the work, but can miss matches unless you tune how thorough they are. The trick is to measure a baseline, add an index, then tune one or two knobs until speed and recall meet your needs. We will build a small pipeline that checks pgvector, runs an exact nearest neighbor to set a ground truth, adds an IVFFlat index, and experiments with probes, and finally adds HNSW and tunes its search parameter. This gives a repeatable recipe you can apply to your own text corpus and queries. First, we verify the database and extension are ready. This snippet connects to PostgreSQL with psycopg and verifies pgvector. It opens a local database connection using psycopg.connect, which returns a reusable con you'll keep for all later steps. A cursor named cur is created to run SQL statements. The create extension, if not exists, vector command ensures the pgvector extension is present, so you can use the vector type and distance operators. A simple select from pg extension fetches the extension name into the variable ext as a final check. The printed ext value confirms pgvector is enabled, which means the upcoming indexing and search examples will work correctly. Next, we run a baseline exact nearest neighbor to get ground truth. This example builds a tiny dataset and runs an exact L2 nearest neighbor. The cursor cur creates a temporary items table using generate series, storing a small ID, a label text, and two identical vector columns, emb and m2, for later indexing options. The variable qv holds the query vector as a pgvector literal string. The select with order by m by ss vector returns the closest ID and distance, binding qv as a parameter. The variables rid and d capture the best match and its distance, rounded when printed. The printed baseline ID and dist show the exact result, forming the ground truth for comparing indexes. Now we add an IVFFlat index and try an approximate inverted list search. This code creates an IVFFlat index in pgvector and executes an ANN search. The cur.execute call builds IDX IVF on the M column using the IVFFlat access method. Next, set IVFFlat probes equals 1 configures the number of inverted lists to probe per query, trading recall for speed. The select with order by EMB vector issues a vector search that can utilize the new index when beneficial. The variable IVFID captures the top match returned by the approximate plan. Lower probes reduce CPU and I/O at the cost of recall, while higher probes improve recall with added latency. The printed IVFFlat ID shows the retrieved neighbor under ANN settings. Then we test how changing probes affects stability and recall. This example compares IVFFlat results as you raise the probe setting. The cursor CUR first sets IVFFlat.probes to 1. then queries for the top 2 IDs and stores them in the list A. It increases IVFFlat probes to 4, repeats the same query, and stores the IDs in B. The expression len set A and set B measures how many results are shared, indicating stability and recall. The lists A and B reflect the trade-off. More probes typically yield better recall, but cost extra latency and memory access. The printed overlap value summarizes how results converge as probes rise, guiding a practical speed-quality choice. Finally, we add an HNSW index and tune how aggressively it searches. This code adds an HNSW index and tunes EF search for query quality. The create index statement builds IDX HNSW on the M2 column using the HNSW method, enabling hierarchical graph-based search. The set HNSW.EF search equals 40 adjusts how many candidates are explored at query time, balancing recall and latency. The subsequent select orders by M2 and QV, allowing PostgreSQL to use the HNSW index to retrieve the nearest neighbor efficiently. The variable hid captures the top result, showing HNSW's output under the chosen EF search. Increasing F search generally improves recall, but increases work per query. The printed HNSW ID confirms HNSW returns a strong nearest match. In a real project, you swap the tiny table for your text embeddings and run the same checks. Start with exact search to get ground truth. Add IVFFlat for a fast, cheap sweep. Then add HNSW for a higher quality ANN option. Measure latency and recall on representative queries before you decide which index to apply to production. Recap. This is a practical pipeline to choose between exact, IVFFlat, and HNSW indexes. Use it when you need faster embedding search, but must preserve result quality. One caveat: approximate indexes require tuning, and wrong settings can silently drop relevant hits. Next step, run a probe sweep to map latency versus recall for IVFFlat across your query set. If short practical IR helps, subscribe and watch the IR videos.